So let me actually start, instead of with the pig, by thanking my collaborators in this project. So Wes Tansey is a PhD student in computer science at the University of Texas, and Sammy Koyejo and Russ Poldrack are in the Department of Psychology at Stanford. So they are neuroscientists, and they're the collaborating experts in neuroimaging, which is one of the major applications of this methodology. So let me start with this picture here. Which I'm red-green colorblind. This is not a great picture for me. This is kind of a dispiriting reminder of my chromatic inadequacies. But for those of you that are not, so one of these colors is red and one is green. And what you're getting here is a set of two sample t-tests between epileptic patients and non-epileptic patients. Every cell here is a particular area of the brain. And this is from a diffusion tensor imaging study. So you can imagine just testing cell by cell, are there structural differences at this particular location in the brain in the two populations? And the color and the shape of those voxels there is giving you an indication of the magnitude and direction of statistical significance for that two-sample t-test. Okay, and you notice some obvious clustering. Here's some sort of positive significant statistics. Here's some negative significant statistics, and so forth. Okay, so that's kind of one motivating example. Here's another one, also from neuroimaging, except now functional as opposed to structural neuroimaging. This is from an fMRI experiment on working memory. I like this data because this is actually the brain of one of my collaborators. Russ Poldrack gained some notoriety in neuroscience for scanning himself every day for a year. And taking not only a healthy dose of radiation, but also a lot of data on things like his mood and caffeine consumption and all sorts of cool stuff. This is just one little slice of his brain from one of those days when he's doing an experiment on working memory. So each little voxel here is a typical fMRI image. The task here is, you'll see one particular task that's an easy spatial working memory task, and then another task that's a hard spatial working memory task. And the visual weight here is something that's proportional, again, to like the z-score from a two-sample t-test. Okay, and again, as in the previous problem, you see some clear structure. The brain is sort of lighting up differentially in these regions that functionally differentiate the easy from the hard spatial working memory task. So in both of these motivating examples, there's a lot of common features. Okay, so in each of them, we have a multiple testing problem. There's lots of z-statistics. We want to know which of those z-statistics correspond to signals or significant tests, and which of them correspond to noise, the ones we don't care about. There's an extra wrinkle here that's not common to most classical approaches to multiple testing, and that's the spatial structure. And I would claim that existing approaches for multiple testing are good at controlling desired error rates, whether it's something classic like Bonferroni correction or something more modern like a false discovery rate, but they're not necessarily so great at leveraging the extra source of information contained in the spatial structure. Okay? And that's what this talk is about. Okay, so I'll give you an outline here. I'll introduce kind of the general framework, the way that I think about multiple testing from a Bayesian and empirical-based perspective. I will give you the basic idea of our procedure, FDR smoothing, and then I'll go into some of the computational and a little bit of the theoretical details surrounding this model. Okay, so here's the one slide of background on multiple testing in high-throughput settings. So if you imagine this conceptual 2x2 table, where the state of nature for every single test of significance, there's either an HI equals 1, that's a signal, HI equals 0, that's noise, and then there's our decision. And so we can imagine this conceptual 2x2 table and think about various quantities involving the entries and the margins of this table that correspond to error rates that we'd want to control. So classically, for over 100 years, people would have been interested in the family-wise error rate, which is simply the frequentist probability that this cell of the table right there is something above 0. And that's what Bonferroni correction, for those of you that know what that is, would attempt to control. For the last 20 years or so, that's not really the error rate that's been the focus of most applied work. Rather, it's been the false discovery rate, which is the following expectation. If you take this entry, which is the number of false discoveries, so the true noise cases that we actually declare to be a signal wrongfully, divided by the total number of discoveries, we would call that the false discovery rate, or more specifically, we would say that the frequentist expectation of that quantity is the false discovery rate. And this is a very interpretable quantity. It's the corruption fraction. If I, as a statistician, am going to give you 100 cases and say, these are the ones that I think are signals, if I'm controlling the FDR at the 10% rate, I'm going to guarantee that an expectation no more than 10 of those 100 are false discoveries. Okay, and that's what our procedure is going to be designed to control, just like some classic approaches, like the most famous being the Benjamin E. Hochberg procedure. We're actually going to connect with a line of thinking on this that's primarily due to Brad Efron, based on the following empirical Bayes model. Okay, so here would be a Bayesian formulation, and ultimately we'll take an empirical Bayes approach. Let's say that there's two groups out there. There's a group of noise observations, and I'll say that the z statistics for all of those tests arise from some distribution f naught. And then there's a signal distribution, and the z statistics there arise from the distribution f1. And all that we don't know in this problem is the mixing fraction, c. So presumably that's something small, 1%, 5% maybe, and the vast majority of all z-scores are coming from that component over there. And you can imagine that this two groups model would come from the following classic formulation of the normal means problem. I guess that should be a zi rather than a yi. That's a little typo there. But my zi's come from theta I plus error, and the distribution of the error is f naught. And then my theta i's are either 0 or they're drawn from some prior distribution pi of theta with probability c. And it's pretty simple to observe that the f1 in this formulation of the model is just the convolution of the noise model here, f naught, and pi in this model right here. Okay? And if you knew what f1, f naught, and c would be, it would be obvious what to report if you're a Bayesian, which is the Bayes oracle probability, just saying, as the oracle, we know what the values of all the unknown parameters are. Let's just take the posterior probability that the true state of nature is a 1, that this corresponds to a signal, namely it came from this mixture component up here. Okay? And the empirical Bayes approach, popularized by Efron and a number of others, is to say, we're not the oracle, we don't know what those quantities are, so let's plug in estimates for f1 and c, and call those c hat and f1 hat. And you notice there's no hat on f naught here. That's usually known. It's, say, if it's a Gaussian test or a two-sample t-test, you know the distribution of the test statistic under the null hypothesis. Okay, so f0 is usually known from theory. And so this is a really nice way of handling the multiple testing problem. I like it in particular because it offers a methodological unification. Both Bayesians and frequentists can agree on the actual procedure to run here. And it's simply a difference of interpretation. The Bayesians are going to interpret that quantity wi as a posterior probability. And frequentists can interpret as something called a local false discovery rate, from which you can back out a frequentist false discovery rate using this bound right here. So I'm not going to talk too much about the derivation of that. I'll show it in pictures here in a second. But I'll just point out that this mapping between the local false discovery rates and a frequentist estimate of false discovery rate is actually, it's biased upward as an estimate of the true frequentist false discovery rate, which means you're conservative, which is a nice feature of this. Okay? And so what's nice about this formulation of the multiple testing problem is, it has all of the nice frequentist properties that you would like to be able to guarantee, but it also is fully conditional in the sense that the measures of significance you get aren't simply a binary decision, yes, it's in the significance set or not. You actually get a measure that's more sensitive, right? It's going to be something that's dependent on the actual value of the test statistic. It'll be more extreme for a z-score of 10 than for a z-score of 3. Okay? This is the picture version of that equation that I just wrote. So if you want to think about the mapping between this model-based formulation of the problem and a frequentist false discovery rate, this sort of set of nested histograms gets you that picture. What I've got here is the histogram that's just my distribution of the test statistics. And what you've got here is the estimate that comes out of Efron's procedure of the alternative distribution of the test statistics. Right there. And that's a subdensity, so it's something that integrates to C. If you recall what C is, that's the prior probability of a signal rather than a null. And so this, say, integrates to 0.05 as opposed to 1. And if you think, all right, let me focus on just some arbitrary bin in this histogram right here, and I'll just say, all right, let's look at that bin right there, and I'll call every single z-score that landed in that bin a signal. It's pretty obvious that the false discovery rate is just going to be the fraction of the white area as a fraction of the total area of that bin right there. And so if you want to see the mapping between the frequentist false discovery rate and the Bayesian quantity here, all you have to do is just find the cutoff right here, which I've drawn with this little triangle right here, where the cumulative fraction of the white area outside that threshold is 10% or 5% or whatever your desired false discovery rate is. Okay, so that's the mapping between the Bayesian and the frequentist quantities right there. And that, that's a pictorial version, but it's easily formalized in a theorem that's due to Effort and Tibshirani about 15 years ago. All right. The problem with this basic formulation of the two groups model is just that it ignores the very obvious spatial structure of the problem. We expect the significant test statistics to be, in some sense, nearby on the graph or the grid or in whatever covariate space we've got. And so our task here is to use that spatial structure to maintain a given false discovery rate, but improve power over the basic formulation of the two groups model. Okay? So here's the approach that we've come up with. We call it FDR smoothing because it controls the false discovery rate, but it does so by spatially smoothing those underlying prior probabilities that I formulated in the model. Okay? So let's say that every test statistic is associated with a node in an undirected graph. So in the fMRI problem, the simplistic version of that would be to say that every voxel is a node in a three-dimensional grid graph. That's actually not what happens these days in most neuroimaging experiments. They actually try to represent the underlying folded two-dimensional topology of the brain, right? If you think of the brain as actually a very, very complicated two-dimensional surface that's folded and crushed in lots of folds. They try to reconstruct the two-dimensional topology. It's some of an uncomfortable phrase. They call it exploding the brain. At least Russ Poldrack calls it that. So so you explode the brain and basically represent it as a two-dimensional graph that sort of lives on the surface of the two-sphere. All right, so it's not actually the topology of three-dimensional Euclidean space. And that's why we formulated this problem as if there's a generic graph with vertex set S and edge set E, even though kind of the toy version of this would be the three-dimensional grid graph. Okay, and then what I'll do is I'll introduce, if you recall the original two groups model that said, we had a distribution of test statistics that are significant, F1, and the insignificant ones come from F0. Before we had a global C that just said, hey, everything's exchangeable a priori. We just know that there's some fraction that come from one population versus the other. Now I'll be very extravagant, and I'll say that there's a different value of that prior probability of coming from the signal population at every single site in the graph. Okay? And this is obviously going to be very, very over-parameterized without introducing some additional structure. And so that structure will come second. But just for now, just let's roll with it, and we'll parameterize these prior inclusion probabilities in terms of this underlying graph of log odds, beta I. So beta I is going to be my choice variable here. That's the log odds of coming from the signal population at site I in the undirected graph. All right? And so our procedure, FDR smoothing, is a way of estimating that underlying spatial field or graph of log odds in light of the observed z-scores at each of those nodes. Okay? Now, it's motivated in terms of this Bayesian model, but it's definitely not a full Bayes analysis. There's a lot of computational there's a lot of trade-offs made that are made exclusively for the purpose of computational simplicity here. We thought a lot about fully Bayesian analyses of a model like this, and it just gets unwieldy very, very quickly to the point that basically nothing you do works at the kind of scale of a very kind of run-of-the-mill fMRI image of a 128 by 128 by 128 set of voxels. Okay? And so what we're doing is much more like an empirical Bayes approach. What you do get fully Bayesian measures of uncertainty at the level of the hypothesis. So you'll get posterior probabilities, and an individual z-score comes from the signal population. But what you don't get is a full posterior distribution for this underlying surface of log odds. Okay, so there's going to be, this is the sense in which in empirical Bayes you can think of this underlying graph of log odds as a nuisance variable, and we're going to plug in an estimate for that spatial field subject to a penalty that enforces spatial smoothing. Okay, and just to give you a toy example to show you that this works, here's a simple 128 by 128 two-dimensional grid graph, and if you squint, you can see that there's a region over here where there seem to be more significant z-scores, and another region over here. Okay, but it's not like this is a monochromatic block. It's not like it's a classic total variation denoising problem or something like that. That's the truth, and this is not the underlying true image. This is the underlying true field of prior log odds. Okay, so what happens in the background, I'm basically drawing every single z-score in the background here from a standard Gaussian. And then I'm drawing these here. Here about 90% of those cases come from something heavier tailed than a standard Gaussian. And here about 50% of them come from something heavier tailed than a standard Gaussian. So these are plateaus of enrichment in the background where lots of the test statistics are significant. Yes. F1 here, so good question. F1, just in a sentence, F1 is the distribution of the test statistics that are significant. Oh, I think for this toy example, I picked normal 0, 3. Right, so it's just a little heavier tail. And that's what we'll reconstruct using our procedure. Okay, so this works pretty well, and this happens in a millisecond. It's pretty fast. Okay, and here's the you can maybe see what's coming for those of you that know a lot about image processing, which you guys tend to know a lot more than me about image processing. But if you just think about the negative log likelihood implied by our two groups model, here's the F1, here's F0. And here is expressed in terms of the log odds, the prior probability of being from this component versus this component. This is just the negative log likelihood of that two-component mixture model. And I will learn what these underlying log odds are by minimizing this objective right here. So I've got a classic kind of total variation penalty, not on the z-scores themselves, but in this latent field of log odds. Okay? And we solve this optimization problem, and what comes out is the empirical Bayes estimate of all of those betas. Okay. So this is superficially similar. Yes, question?
I don't understand. You don't know F1.
I don't know F1, so we have to estimate F1. And that's something that I'm happy to talk about at the end. To be honest, F1 is it's something that looks, and I agree, it looks like it ought to be very significant in this problem. It turns out to be very simple to handle, and that the performance of the overall method is extremely robust with respect to different ways of estimating F1. And I'll give you a slide at the end that I hope is a little bit more convincing than just my saying so. Okay? But you're right that this hangs together only when you've used a plug-in estimate for F1. And I hope you'll believe me that the plug-in estimates available for F1 are actually very efficient in this particular setting. Okay, and people that would know a lot about this, the paper in particular that we use to estimate F1 is a paper by Sergio Tokdar and Ryan Martin using a technique called predictive recursion. Okay, so we can chat more about that offline. All right. Yes, question. That's correct. No. So the question is, does the computation increase in complexity significantly for a more complicated graph? And the answer is basically no. The algorithm I'm going to show you that we use to fit this works for an arbitrary graph structure. And in that way, it's sort of algorithmically different from the classic approaches you would think about for TV denoising. Okay. And I will bring out some similarities and differences from some familiar things here. This looks superficially similar to two things that you are probably familiar with. So one obviously would be total variation denoising. If you think about this basic model here, the key difference, and it looks subtle, but it's very, very important from the overall performance of the method. If you think about what total variation denoising would do, you would say the theta i's are smooth, right? And that's not what we're saying at all. We're saying that the ci's are smooth, which is something fundamentally different. So I could have a very, very rough image in theta I space. I could have a whole bunch of adjacent test statistics, some of which are very negative and some of which are very positive, that average out to 0. And total variation denoising would not find that plateau, and this would. Okay, so there's a very significant difference between saying the theta I is smooth versus the Ci is smooth. And something that's also similar to is a very recent literature in machine learning on a technique called, or a suite of related techniques called graph-based anomaly detection. So I'm thinking in particular of some work by Emmanuel Candace and some folks at a CMU, a guy named James Sharpnack, who's a new professor at UC Davis. And they're working in the following domain. I know that all my z-scores come from this basic model right here, but there's an anomaly set S, which is a subset of nodes on my graph. And whenever, for whichever nodes are in S, the theta I is mu, and whichever nodes are not in S, theta I is 0, and I just want to find the anomalous set S. And so what's immediately different about that problem is that every single anomalous theta I is the same number, right, which is very different from our false discovery rate kind of setting. So it's superficially similar to both of those problems, but quite different in terms of the algorithms that you would use and the performance of kind of an algorithm designed for one domain applied to the other. Okay. All right, so if you recall our objective function, there's a lot of important details about this. And I say that I'm not going to cover F1. I'll cover F1 in the end if you want, and I have sort of an extra slide for that. What I'm going to talk about for the rest of the talk, the 10 minutes I have left, is basically just solving the optimization problem for a fixed choice of lambda, F0, and F1. Okay? So we use an EM algorithm to solve this. The objective itself is not convex, but there's a very simple set of latent variables that I can introduce, which those latent variables are simply the latent indicator of whether an individual z-score came from the signal or the noise component. Conditional on those latent variables, I have something that looks like a I would say a logistic regression, except there's no regression. It's just a IID, or not IID, it's an independent binomial model parameterized by log odds, where the beta i's are the log odds right here. So this is convex, it's separable, and it's linear in these HIs, which are my missing data. So it's very easy to do the E step in an EM. So the hard part is the M step in the EM, because what I've got in the M step is this objective right here, which is nice, smooth, convex, very easy to work with. But then this term over here, which is just the sort of matrix representation of that vector of first differences across the edges of the graph. Okay? So this is a very, it's easy in one sense because it's convex, but it's hard in practice because it's a very large problem. We could have on the order of 10 to the 6th, maybe even some settings 10 to the 7th nodes in the graph. And this penalty function over here is known to introduce a lot of difficulties into classic convex optimization routines. And so our kind of overall step looks like this. There's the E step. We'll handle the likelihood here, which, this is the pretty standard step. We'll handle the likelihood bit using just at every iterate using a Taylor approximation. So now we're ended up with something that looks like a weighted least squares plus penalty problem. And all of the effort here is in minimizing this kind of surrogate objective of a quadratic function plus this total variation penalty. And there's too many algorithms for solving penalties or penalized likelihood problems of that kind to list here. I've just listed a selection of them. I will make the point that none of them are especially fast in our context, which is the weighted least squares objective, which is different in some important ways from just an ordinary L2 loss, and an arbitrary graph with no notion of distance underneath. Okay, so in particular, some other fast things like parametric max flow, they don't work for this problem, or at least they don't work off the shelf. There'd be some heavy lifting to make them actually work for this problem. And so we had to come up with something that worked a lot better for these in order to make this appropriate. In other words, to make it something that we could call again and again and again in the context of an EM algorithm. And so here's what we came up with. We improved, just for the basic total variation denoising problem, we improve on what we think is the best of what's out there via a very simple slack variable strategy. Okay, so here's the slack variable strategy. We leverage this theorem, which is a basic result in graph theory, that says you give me an arbitrary graph, and this is now addressing your question about the complexity of the computations with respect to a grid graph versus an arbitrary graph. You give me an arbitrary graph, and this theorem says that I can take that graph and write it as a union of trails, where the number of elements in that union are precisely equal to the number of odd degree vertices in that graph. Okay? And the proof of this theorem it's the best possible proof because it's exactly constructive of the algorithm that allows you to find that union. Okay, so it's a really nice proof. And here would be an example. If here's my two-dimensional grid graph, here's my union, right? These 3 trails plus these 4 trails right there. That's actually not the optimal one according to this theorem, but it's an obvious one for the grid graph here. And the point is this theorem says that for an arbitrary graph, I can find such a union, and I can do it in linear time. So it's a really simple pre-processing step. It's not max float min cut. No, it's not the Chambon and Darbon paper. It's different. We should talk afterwards. So what's the significance of this union of trails idea? Well, let's just say I had to solve it on a single trail, right? Just a one-dimensional chain graph. That's something I can do in linear time. Okay, and there's at least two good algorithms that I'm aware of for doing that. There's one called the taught string algorithm, and then there's a dynamic programming algorithm that essentially makes solving the fused lasso or the total variation problem on a chain graph equivalent to doing a Viterbi-style algorithm. So it's very simple. And so if I've just got one trail, I can solve the fused lasso in linear time exactly. So it's there's no epsilon, right? It's just an exact solution. And so here's our slack variable strategy. We'll take that theorem, and we'll say, let me rewrite this penalty as my sum over the trails. So this is my outer sum over the trails. That's the union that the theorem guarantees exists. And this is now a sum over the edges in that trail. So this is just a one-dimensional chain graph as an inner element of this outer sum right here. And then for every trail, we just introduce an appropriate number of slack variables that says the node basically just counts the duplicate nodes that enter into those trails. And so we formulate this just as a simple constrained optimization problem, and then we use ADMM to solve this constrained optimization problem. And what's great about the ADMM update steps is because of these nice algorithms that enable you to solve the fused lasso in linear time for a one-dimensional chain graph, every single update, primal, dual, slack variables, they're all linear time in the number of nodes in the graph. So the only thing left is to sort of see how quickly this converges. And I'm not going to talk about the convergence, like how many number of iterations that this takes. But I will say that this is, just empirically, we've observed this to be faster than anything else that's out there. Okay? And just to give you, an example in a real data set here from Russ Poldrak's brain. Here's that image that I showed you at the very beginning. And if you just use element-wise Benjamini-Hochberg, which is the classic method for controlling the false discovery rate, these are the Z statistics that you flag as being statistically significant at the FDR equals 5% level. Okay, so fair enough. There's clearly some structure here, but it's also suboptimal in some obvious ways. You get all this corruption up here that's just not believable from a neurophysiological perspective. And then, oops, wrong. There we go. And then here's our method. So you kind of clean up all the mess out here, but you discover more significant test statistics in the regions of interest. So it really does have exactly the performance that you would hope, namely spatial smoothing. And in the last 2 minutes, I will just say one quick slide about the theory of this procedure. I'm not going to quote you a theorem. I'll say what the theorem is. Okay. So what I've given you here, so remember there's the lambda parameter. There's the lambda that enters in any kind of total variation regularization. That's the strength of the total variation penalty. Here's what you get for this. Here's a one-dimensional chain graph. And so here's the region where the z-scores are significant. Here's another region where they're kind of significant out here. Here's what you get if you run our algorithm at lambda equals infinity. Right? And at lambda equals infinity, what you reproduce is exactly Efron's model, the classical two groups model, with a single prior inclusion probability for all test statistics. And then here is the truth as a function of the location on this one-dimensional chain graph. Okay? So the theorem is that there's an open-ended interval. In other words, it's half open. There's, the upper end is infinity, of possible values of lambda for which the reconstructed prior probability is sandwiched in between the truth and the lambda equals infinity solution. Okay? And that fact is sufficient to guarantee that this does no worse than the ordinary two groups model. Whereas in practice, it does much, much better than the ordinary two groups model because it's sensitive to local structure in a way that the two groups model cannot be. Okay? So rather than kind of bore you with tables and theoretical details here, I'll go ahead and quit and thank my collaborators again and point you to the paper and the code for this, which are up on Wes Tanzi's website. So thanks very much.
Right, we have some number of questions.
Hi, James. So you're using this fused lasso penalty. In the spirit, it does something very similar to an Ising model on your grid. And I'm wondering whether you've considered other graphical structures, like, for example, a logistic Gaussian process or random Markov random field. I mean, depending on how big your problem is, I don't know how many voxels there are, but there seems to be algorithms that allow you to do fully Bayesian sampling on those fairly simple graphical structures.
Okay. I don't know that I would agree for Gaussian process. Right. Okay. So I think Gaussian process is just, yeah. So for something like a Markov random field, a conditional autoregressive model would be a simple example. We initially kind of looked into thinking about a car model on these prior inclusion probabilities. In our experience, it's just that the models are kind of flaky. They're hard to elicit priors for. There's kind of an unintuitive phase change in terms of the autoregressive parameter in a car model where you get good performance on one side and then it just totally crashes. So I'm hand waving here in terms of our own initial explorations, but maybe we just did them wrong, but we didn't find them that promising initially. We certainly didn't see that there was a potential there for drastically better statistical performance given the computational requirements of those. Namely, just the biting the bullet and doing a full MCMC, a side at a time update in a Markov random field or a car model or something like that. I'm fully prepared to say, yeah, sure, the fully Bayesian model would beat it if you could get the computation in order. We just didn't go down that route.
All right, Nick, you had a question?
So you mentioned James Sharpnack's work.
Yeah.
Which at least one of the differences there is that they basically always assume F1 is a point mass, right?
Yeah, that's right. That's right. So not necessarily a point mass, but it's a convolution of a Gaussian and a point mass, right? So it's just another Gaussian.
Yeah, sure. Yeah. What I was wondering is, that's true. I understand that. But from what I recall, they're able to there's a recent paper with Airy where, from what I recall, they're able to achieve some really impressive SNRs that are sort of hard to believe even, and precisely because they do some very careful analysis of the scan statistics, stuff like that. Yeah. So what I'm wondering is, despite this limitation, and I think their algorithms are also limited to that, the point mass condition. But despite that, do you think there's anything there that is statistically sort of, let's say you were able to assume the same thing, right? Would their methods be doing something better here? And if so, do you think there's any possibility of incorporating those kind of approaches to get better SNR here?
Sure. Yeah. I mean, the line of papers you're talking about, very cleverly designed scan statistics, great papers, right? I really enjoyed reading those. I do think that the limitation of a single value of the underlying alternative hypothesis for all anomalies in the graph is just not scientifically feasible for some of the problems that we're interested in. I would just say that the different problems, right? There's one giant anomaly on this graph. And everything, it's sort of a homogeneous anomaly as opposed to a bunch of heterogeneous anomalies that are kind of not all there in this region of the graph, but statistically enriched in this region of the graph. So I do think that they're trying to solve different problems. Whether you could sort of generalize some of the very promising results that they have for that scenario on the basis of their scan statistics for this problem, yeah, I would be very very eager to see whether that could be done.